Hey guys, in this video I'm going to build a little bit on what we did in class to show you how you can find the force that a spring applies when pulled apart by using the work energy theorem. So we've already studied that a spring has some energy when you pull it apart, it has some potential energy stored in it, but we haven't learned about how much force it takes for me to actually hold this spring apart. And so what I'm going to do is try to find that out by using work energy. And since we're studying work energy, this seemed like a good topic to talk about right now. So what I want to do is I want to think about what happens when I pull the spring a very small amount, so some delta R, and that delta R should be related to the amount of force times the distance that I'm pulling apart. So that's our starting point, and let's see if we can get to showing the force on a spring.
So the first thing we want to do is recall the definition of the potential energy stored in a spring. That is, the potential energy stored in a spring is the spring constant times the square of the change in the length of the spring. This is the equilibrium length of the spring, and this is however far it's stretched. So now we want to start with just saying that we want the equilibrium length of the string to be 0. So just going to set r not equal to 0 for simplicity. And since we're stretching the string a very small amount, I'm going to say that the initial length is just r, and the final length is r plus dr. So that's the original length plus a very small amount. So now when I go down to calculate the change in the potential energy due to this small amount, my Vf is going to have this r in it, and my Vi is going to have this r in it, which looks like that. And so now just notice that this negative sign comes from the negative sign here. That's not the negative sign up here. I set this to be 0, so the original expression was 1/2 kr squared, which is where this came in when I put it in here, and where this comes in when I put it here. So now I'm going to expand this expression out. So just distributing through there, you see that you have an r squared here, a 2r dr, which comes from the cross term here, and then that dr squared, which is just that guy squared. So the first thing that we notice is that there's a 1/2 kr squared here, a negative 1/2 kr squared, and a positive 1/2 kr squared here, so those guys are going to cancel. And we're left with an expression like this. Now notice there's a term which is linear in dr and a term which is squared in dr. So that dr, that's an infinitesimal in the sense of calculus, which means that dr is much, much smaller than 1. So when you square something much, much smaller than 1, and then you take that dr to be as small as possible, which is the natural thing to do in calculus, this thing goes to 0. So we're going to have this thing canceling and out end up with just potential energy and this term. So this is the change in potential energy if we change the length of the spring a small amount. So now let's write the conservation of energy equation for a very small change in the length, which means that we're going to have a very small change in the energy, which will be equal to the change in kinetic energy plus the change in potential energy. That should be equal to 0. So we have the change in kinetic, and then we use our expression for the potential is kr dr equals 0, and that finally gets us that the change in kinetic energy of an object being pulled by this spring will be negative kr dr. And I should just point out here, just for emphasis, that we talked about this in class, but this k, this is a kinetic energy, this k, this is the spring constant. Not just for this class, but for physics in general, you're constantly going to have to juggle the fact that sometimes we have the same letter representing different quantities. It's even worse in my handwriting, right? This should be a lowercase k, this should be a capital K, and then we could claim that they're different. But when you're writing, it's even harder to tell. So you always have to keep in your head which quantities mean what. So moving on, now we want to use the work energy theorem. The work energy theorem tells us that the change in the kinetic energy of a system is equal to the dot product of the force that you act on with it and the displacement over which it moves. So we're clearly going to want to compare that dk to this dk because they're the same. So somehow f dot dr is negative kr dr for springs. But we need to figure out what the dot product is, and then we just think about the directions that are happening in the problem. So I pulled the spring in that direction, and the displacement was like that. So the spring was displaced in the same direction. So dr is in the same direction as f. That means f dot dr will be the magnitude of f times the magnitude of dr times cosine of the angle between them. But in this case, the arrows are going in the same direction, right there and right there. Cosine of theta is 1, and so f dot dr is just f dr. So now we can combine all these things. We know that dk is f dot dr. We've found that based on the directions, this is f dr. And then finally, from up here, we have that dk is also equal to negative kr dr. Kr dr. And so then just comparing this equation, there's an r here and r here cancel, and then you can solve for f. That force is called Hooke's law, and it tells you that the force that it takes to pull a spring is proportional to the spring constant. It's proportional to the distance you pull it, and it's in the opposite direction. You pull it in one direction, the spring tries to pull back in the other direction.
Okay, so that's how you derive Hooke's law from the work energy theorem. Hooke's law being the force exerted on a spring when you pull it. It's not so important right now what the force on a spring is, but using the work energy theorem is an important part of this part of the class, and it's going to be on the next exam, so it's good practice to see where we can get these kind of things from work energy theorem. It's also important because we have no way of getting what forces are without doing experiments. We could have done an experimental setup with this spring and figuring out how much force is on it, but it's nice to see that based on what we know about work and energy, we can derive the force on a spring. So you don't necessarily need to just go out and do measurements to understand things about physics. You really can just sit there, work on a piece of paper with results that you know already, and figure out new things about physics. And that's really what physics is about, using the model that you have already and coming up with new results. Okay, so that's all I wanted to show you about this video. Thanks for watching, and I will see you guys next class.